Hey everybody, today we're going to take a walk down memory lane. We're going to go through the history of manipulators in Trossen Robotics. We thought it would be fun to pull out all the old arms and kind of take a look at the history and the different evolution levels of the arms throughout the years. For me, this is like opening old journals. This is literally 20 years of history in this company. We went up into the attic and we started opening up old boxes labeled museum. Because over the years, we would just grab arms every now and then and throw them in a box and say, someday we're going to want to look at these. These are going to be fun memories. So what I'm going to do is I'm going to walk through sort of the evolution of the arms from 20 years ago up to today. And I'm going to talk about like design considerations, what were some of the constraints we had at the time, what kind of tools do we have available, and just sort of talk about it. And it's going to be a fun exercise to look at like design and engineering choices from prototype to making products. This here is a Lynxmotion Robot Arm. This is actually kind of pre-Trossen Robotics. This was a company that was making hobby and educational robotics back when I started the company in 2004. So Lynxmotion is like one of the OGs that's out there. It was them and Crustcrawler. They were the two companies that were kind of battling it out in the market. Fun fact, they hated each other's guts. It was kind of funny. We carried their products as well as a lot of people. So when Trossen Robotics started, we were basically an online store. We were like a mini Amazon for hobby and educational robotics. And so what I did is I reached out to everybody in the market worldwide that was making robotics components, whether they would be wheels or motors or servos or bracket systems like this, like erector set systems. And we just started putting it all in the store and carrying it all in one place. That was before we started actually like kitting things and whatnot. We were just a reseller essentially. So you had Lynxmotion and you had Crustcrawler. And the guy who owned Lynxmotion used to call him Crud Crawler. He was a very ornery old man. And then the guy who owned Crustcrawler loved poking at Jim anytime he could, but they hated each other. They made an erector set like this. It was all made out of metal. They created it using high-tech servos. So back in the day, everything was made out of hobby servos. That was available at the time, and nobody was making robot-specific servos. And these are low-cost planetary gear servos that all the robotics kits were built around. Lynxmotion went with a modular system. You can see that they have bar links in here, which is really low cost because these things cost like 50 cents to make. And then they've got modular brackets that can kind of be combined in any way, kind of like a Lego set. So if you look at their catalog, you can see that they made a lot of different types of robots out of all the basic same components. You can see that same philosophy over at Servo City. They have a huge array of parts that you can build anything you want out of. You'll see it in our X series arms that we have some modularity there as well. And fun fact, Lynxmotion was bought by a robot shop, and so they still make some of these robots or the next generation of them. This here, I can't believe we still have this thing. This is one of the first arms we ever made in-house. This is actually on a wood platform, that's how old it is. And this was cut on our very first laser machine. We bought an American laser machine. I think we bought it half price for 25 grand, and we were still ripped off. I think that it was street price was $50,000 for a low wattage laser machine, and you could buy them overseas for like 20 grand at the time. So we really overpaid for it, but it got us up and started. And we started by cutting ABS. So if you look at this up close, you can see that this has a lot of texture to it. ABS is good to work with if you want to cut, drill, tap, but when you cut it on a laser machine, it's really dangerous. We set the machine on fire 2 different times. I was driving to work and there was a fire truck in front of me, and every turn I took, it turned with me. And I'm like, would you please get out of my way? And then it turned onto our block, and I thought, please no, please no. Then it pulled into our parking lot and then parked right in front of my building. So I walked into work to find out the building had been set on fire again. So we, at that point, decided we were never building with ABS again. It was too dangerous. It's also really gunky and it's not very accurate. It's good for hobbyists to build with, but not so great for a product where you need a lot of reliability. We just wanted to do a theory of basically servo layout. When you first build an arm, you can do all the math you want, but until you lay an arm out and put servos at certain positions and have your lengths laid out, you won't know how strong it is. You just have to do trial and error, we found. And so we wanted to size the arm and see, can this lift anything? Is it big enough? Once you've done that, you might realize that like, oh, these servos are overheating, so this is too much weight out here. Shrink your link down, same in this section here. So when you do your first run at something, you really don't care how you build it, you're just putting your servos in place. So this arm uses AX servos, which are sort of the hobby level robotic servos of the old generation. And they had the MX ones that are a little stronger. These used a rail system that go around the servo, and then you'd have to put nuts on the back of the servo. That was a pain in the ass. So if you can see on the back side here, you've got these rails and the nuts that you have to like squeeze in with your fingertips. And after you build a few arms, like your fingers are sore as hell by the end of the day. This has one of the very early gripper styles where it's just a single servo with one of the gripper paddles on one side. You will see through the evolution here that we move over to swing arms and a rail system. This is not so great because you're only moving one side. It's hard to pick things up. It's hard to have repeatable code with it. When designing an arm for joints where you need more power, you have to decide whether you want 2 servos or 1. Pros and cons of that are 1 servo is simpler to deal with. You have less mechanics, less brackets. 2 servos can fight each other if you don't have really good code or a deadband where they're not conflicting. But sometimes the next servo up that's the equal strength of 2 smaller servos is too expensive. And so it's better to just stick with 2 low-cost servos in the bottom. This is what we ended up making. And so you can see we dropped using standoffs, which was a stupid idea, and instead made sheet metal brackets. This is similar to something you'd see like on a Lynxmotion arm where you have bent sheet metal, and we used a similar methodology. The reason you use sheet metal is that you can get really strong 90-degree angles, but they're very cheap. You can have a bracket like this made for like 50 cents when you're making them in quantity. You can do extra bends on here to strengthen them, and they're really easy to build with. We still have a bunch of flat plastic in here, so we actually have a spacer in here that's just a stack of acrylic inside. Got some of that going on up here, and then you have it in the base as well. So back then, we basically only had a laser machine and the ability to buy low-cost metal brackets. When you're designing, you have to think about design for manufacturing, and you have to think about the materials and the machinery that you have access to, and you have to balance that with costs. All we had was a laser machine in the building, and so everything was being designed around flat acrylic. There are a lot of restraints to that because you can't really do 90-degree turns with acrylic. So if you look at the old arms, you'll see that it's standoffs and flat plates, you know, top to bottom for all of these designs. And we had to design that way because we hadn't yet built anything with CNC. We didn't have the money, we didn't have the design shops at the time, and it was very expensive to do. So if you need to make like a 90-degree setup on it, you would have to do like a tab and slot methodology here, right? We got a call from a customer one day and he says, I can't assemble the kit, it won't go together. And he says the tabs won't fit into the slots. So we went and looked at all of the kits that we had made and started trying a bunch out, and all of a sudden they weren't fitting together, or if you got it in there you had to jam it, and acrylic's brittle so they would break. And we were like, what the hell is going on? Like, we were really careful when we designed this stuff. And so we grabbed some calipers and we went and we were checking all of the acrylic plates and found out that there's up to 1 millimeter variance from one side of an acrylic sheet to the other. And so of course we were really angry about that. We call up our vendor and we're like, your tolerances are terrible on your acrylic sheets. We can't build with this stuff. And they say, of course, that the tolerances were within spec. If you check the website or their data sheets, that they do say they can vary quite a bit. I remember talking to the rep and he goes, Matt, we sell plastic to sign makers, not roboticists. You're not supposed to be building robots with this stuff. And I was like, okay, well, I guess that's a fair point. But we learned a lesson there, which is know your materials and don't design materials that can't stand up to the spec that you need. So we had to throw this out pretty quick. So there's, I don't know how long we were doing it, maybe a couple months or maybe a year or something, but if you find some old pictures on the internet, you'll see the old tab and slot method. On this old arm, our controllers were underneath. These used to have the RoboticX controller inside them. That was basically an Arduino level controller to control the arms. This was the first generation that we put these parallel grippers on. So this has little rails on it, and it has some swing arms inside. And this is a way that a lot of arms were built in the hobby world for decades. These arms here are RobotGeek arms for, I almost want to say a brief time, but it wasn't brief. I think we tried to launch RobotGeek for like 5 years. This is back when Arduino exploded and got really popular. And at the time we were selling to hobby and research and education. but we didn't really have a low-cost version of our kits that could be more hobby or like K through 12 education. So what we did is find a servo company where we could customize the case and put the rail system on these, and then use the bent metal bracket method, and then we used Arduino. And we made our own version of the Arduino called the Geekduino, and then we made our own breakout shield, which laid all your I/O out in a really nice, easy to use hat or shield. And then we had a bunch of modular components that you see everywhere these days. I still think it's a good business idea. We just never had enough time or money to throw at it. And at the time you had other companies that were blowing up like SparkFun and Adafruit, who just did a killer job of filling the niche. And there were other more simplistic robots on the market, one like Easy Robot. And it was hard to launch the product with all the noise that was in the market. And we just sort of failed. Like we just couldn't get enough momentum or make enough noise ourselves to sell a bunch of these. I think that little experiment lasted about 5 years, and then finally, after many people tried to convince me many times, we took it out behind the barn and shot it. This was generation 1 of Trossen Robotics, probably the first 5 or 7 years of the company. Let's move on to generation 2. The very first prototype of generation 2 was probably this one, or one that looks just like it. This is when 3D printing really started to become a thing. It became more reliable, the price on it came down, software was getting better, it was getting easier to use. So we started experimenting with 3D printing our brackets. And the idea was to go to an even more modular approach that was a little bit more robust, a little bit better looking, and then be able to make larger arms and make use of larger servos. This is actually when I started learning CAD. So before this, I would just design with an engineer, and we'd do it like on paper and discuss it, but they would do all the designing. This is when I actually started getting my own hands dirty and learning Fusion in the old days. And it was really fun, it was really exciting. This is also why you'll endlessly hear me preach about that there's no excuse why you can't learn anything these days, because YouTube exists. I'm so old that I had to learn things before the internet, and you couldn't. You just couldn't pick things up. You had to go to school for those things. And now you don't have to. You can just watch YouTube videos, you can get free software, and just pick a project and go after it, and through trial and error, pick up skills yourself. And that's how I became a mechanical engineer. So this is in an early prototype. So again, the idea is to be modular. And then I started looking at using extruded aluminum as an option for building, with the idea that if I could make a set of modular brackets that could be used with a basic family of servos, I could build from a small little like pincher-sized arm all the way up to a full-sized, what ended up being the Viper X. So we started playing with 3D printers, and we were doing FDM at the time. The idea behind this was to use extruded aluminum and split the brackets so they could mount around it. We didn't get to CNC right away. We started with 3D printing. The reason was it was cheap and it was accessible. At the time, I didn't realize how low cost metal brackets could be. This is the WidowX 200. This is from the X series of arms. What we ended up doing was making arms from $500 up to $5,000. We didn't know what the market wanted, so we decided to make a whole family and just kind of hit all price points, size points, and strength points with the modular system and see what the market would tell us. What we found out was the market liked low end and high end, but there was still some people buying in the middle. But by and large, either somebody wanted like a $500 arm or wanted a $5,000, not so much in the middle. So over the years, we started reducing the line and pulling arms out. This used our modular system with the extruded aluminum bars. My concept behind this was that people could alter their arms after the fact for their own needs. So let's say you need a lot of reach, but you didn't need a lot of strength. You could buy like a mid-sized arm and then cut your own bars, because we buy these from Missimi, so anyone can buy one of these. You could change the length of your arms, or let's say you like the features and the servo choices on one of the arms, but you need more strength, you could shrink the arm down. Much to my surprise, absolutely nobody did that. Nobody altered their arms whatsoever. We also made the grippers on these so that you can alter the fingertips. So the fingertips on our arms have always been removable from the carriages on the rails. And I thought, okay, that's great, because then people can 3D print their own different gripper types. And again, the market told us no one cared. People buy the arm as is, and they would just use it. That really surprised me. I thought there was more people doing customization at that levels. So we added like a feature that we put a lot of time and effort into that the market ended up not wanting. Believe it or not, when these arms first came out, these brackets were 3D printed. We went to market with 3D printed brackets. The reason we had to abandon them is it turns out motors get really hot and 3D printed plastic tends to melt. I remember I was writing code for one of the arms and I was trying to figure out why it wasn't getting to the proper position. It was supposed to be like horizontal and I looked over and it was sagging and I'm looking at it and I'm like trying to debug my code for a while. And then I'm starting to look closer and I pull it up and I realized that the bracket had actually warped because while I was holding position, the servo had gotten too hot. And we were like, I think launching at the time. And so I had like a heart attack because I thought we just spent like 6 months and all of this money building up this entire new line and the product doesn't work. Like I literally can't ship it. So cue like an entire panic team. What we did is we went and bought every type of filament on the market, every type of plastic we could find, and started printing little cubes, and then we started boiling them in the kitchen. We would boil the water to a certain temperature, and then take a pair of pliers, put them in there, and then we would squeeze them afterwards, and we'd see what happened. So some got really brittle and would like crack, some would get like squishy, some would fray apart between the layers, and it ended up, I want to say it was PLA that ended up holding up the best and had what's the highest deflection temperature. And so we ended up going to market with that. I believe the ones that were melting were ABS. Again, ABS, like the bane of my existence. Big lesson learned, which is like, think about all the things that could go wrong when you're designing a product and trying to count for them. But sometimes when you move from like an old way of doing things to a new way, so like the old way, it was all metal brackets. And then we moved over to 3D printing. I didn't really think about the fact that servos could get that hot. So when that happened, I thought we've got to get away from plastic. I said, well, why don't we just take a look at metal parts? I thought metal parts were going to be just prohibitively expensive. So we ended up CADing up some of the metal parts. We sent them over to some manufacturers. This is overseas in Asia. And when the quotes came back, like I was blown away at how cheap it was. It was actually viable. Another evolution that happened back then was we used to sell these as kits and you would assemble them yourself. And we realized that, I don't know, maybe people don't want to spend time assembling them because an entire arm could be like 3 or 4 hours of assembly time. A lot of nuts and bolts to get it done. So we started experimenting with pre-assembled arms and putting them out there. Well, that allowed us to raise the price and then open up our margins so that we could afford more things, more quality, different manufacturing methods. And so that opened up the door to being able to even look at CNC. So as soon as we saw what the price was, I was like, that's it, we're done, we're moving to metal. Like get rid of all the 3D printed parts that's touching the servos. So we still have 3D printed parts on things like the fingers where they belong. We use them on the skirt, we use it on the controller box, but everything else was metal. Here's 4 arms from the X series line. So you can see small pincher, medium-sized ones, the ReactorX and the WidowX 200. I believe this is the WidowX 250, this is the mobile version. And so you can see that we use the same brackets in all of these, it's just got longer sections in between. And then instead of a single bracket, you might have a dual for 2 servos, but it's all very modular. And I believe in the beginning we had 8 arms total for the whole series. Another design choice that we've consciously made on our arms throughout the years is that we don't shell them. They've always had a really raw appearance to them. And when I was designing this X series of arms, I even thought they were kind of ugly. Like using extruded aluminum is not the sexiest or prettiest. And everybody else's arms out there are shelled really nicely, the Cobots, and they've got tubing over them and everything. We've never had high enough quantity to be able to afford that level of tooling. And so we kind of tried to play to that by making the brackets themselves look kind of cool and just giving it its own look and feel. And you know, now it's kind of a signature of ours. Like if you see our arms in labs out there, like it's distinctly a X series Trossen arm. And in the end, they started looking cool. Fun fact though, is that our arms have been in a couple movies, so I guess maybe they aren't that ugly after all. They have kind of a sciencey engineering look to them. The movie Transcendence with Johnny Depp, our arms are in his office in the background. You'd have to really know what you're looking for to see them though. I remember opening week when that came out, we took the afternoon off, we took the team out, we went to go watch the movie, and we didn't know where they were in the movie, so like we're all watching like hawks trying to spot them, and then finally we saw him, and he's being interviewed in his office, and like totally out of focus on the back wall, you can kind of make out our arm. And we were like, there they are! And we all started cheering and everything. And the rest of the theater was like, why are the nerds making so much noise? Like, they had no idea why we were all excited to see these in the background. There was a recent time-traveling horror movie where one of our arms is used in it. Oh, there was another time I was sitting on the couch at home and a commercial came on with Ashton Kutcher, and he was threatening to drop people's phones for something. It was like some gimmick, and it was the RobotGeek gripper that was holding the phone. And I was just sitting on the couch, and all of a sudden, Ashton Kutcher's playing with our robots. I thought that was cool. This is an arm that's made by Innfos called the Gluon, and this came out, oh gosh, 5 years ago at this point or something. I remember seeing this Kickstarter in the morning. It popped up on my news feed, and it honestly scared the shit out of me because I thought, well, there goes my business, because I can't compete with that, because they wanted to sell this for like $2,500, and the features on this blew away anything that we were selling at the time, because these servos are way better than the Dynamixel servos. For longer than 10 years, I've been looking for servos like this in the market, like basically stronger planetary gear motors that can just have more accuracy, lower cost, and a lot more strength. And now that's happening. Now they're spreading throughout the market, and I'm about to show you the new arms which use them. But 5 years ago, they didn't exist. They weren't around. Dynamixel by Robotics was the only game in town, essentially. But this arm popped up. They had a Kickstarter. There's a whole dramatic story behind this thing. Apparently the founders got mad at each other and the whole thing blew up. They never delivered any arms. There was like a smash and grab or something where the offices got raided, and they, like, one of them stole everything from another partner, and then they ended up getting sold to another company. We talked to them because I was trying to get my hands on these servos, and I was trying to design arms with them at the time, and they just never ever got finished. It was like bought by one company, then bought by another, and they just sort of been passed around like a hot potato. Anyway, this is like an early forerunner of the new types of servos, basically QDD type servos that just never saw the light of day. But that arm and Cobots were inspiring us to make our own Cobot-like arm. And so I worked on this on and off for probably a year or more. And the idea was to do a servo layout that was like a desktop Cobot. And so you can see that it sort of follows the same pattern as a Cobot. And this is still using Dynamixel servos, and it's using our modular bracket design. And we tried to make the brackets even more attractive, you know, some better curves to them, and we did some cool anodizing, and we did a blue version, and they really came out nice. And this has a different gripper design on it. This has the rack and pinion design in there, which is really nice because it's very smooth, very accurate, very strong. And I really thought this was gonna be our next arm, but all of a sudden the next generation of servo motors came out, and as soon as those things started hitting the streets, this thing was dead. If you're gonna be an engineer, you've gotta get used to that happening. You gotta get used to throwing projects away. Like, this was my baby. I mean, I have hundreds of arms into this design, and this will only ever just sit on a shelf. And sometimes that's just the way it goes. The market moves, things change, and you have to abandon ideas. It doesn't matter how much you loved them, you have to kill them. And here we are, up to modern day. This is the new WidowX AI. This is what we're selling right now. Isn't she gorgeous? So this arm is using the new servos, basically quasi-direct drive servos. They're planetary gear motors, very high strength, low gear ratios. And this is what the machine learning community wants. Because of the low gear ratio, the arms are very reactive. So when you're doing machine learning, you have to be able to read when you're hitting something, when you're getting resistance picking something up. The compliancy that you have is very important. So that's one of the best attributes of these motors. So you can see that we still don't shell our arms. It's all exposed brackets. We have the same aesthetic that we've used. We've even kind of gone a little further with it because we have a little bit more real estate to make it pretty. There is some 3D printed on here. This is laser sinter designs to sort of close it up, and it uses the new servos. One of the things that's different is there isn't an extra bearing in the base of this arm. This arm is meant to be very compact and very light, and these servos have bearings inside of them that are strong enough, so you don't have to have one in there. In some future designs, if we go a little bit bigger, we might add one back in, but for the moment, that is not there anymore. This does use the new rack and pinion on the gripper, so you have a nice, very accurate, very tough gripper. And this arm is still designed with CNC manufacturing, so you've got big aluminum brackets on this. What's great is it looks good, it's very strong. What's bad is these are really expensive to make. I mean, there's a lot of metal being cut up in order to make this. So where this is headed is injection molding. Eventually this is going to be injection molded plastic. It's going to have reinforced glass in it, or it might have metal brackets behind it, because we don't want to lower the quality at all, but we have to get the price down on this. Basically, the market is demanding that we get as low as we possibly can, because these are eventually going to be like the microwaves and vacuum cleaners of the household eventually. And people don't want to pay for really expensive CNC parts on that. So while it's CNC'd right now out of the gate, we're eventually going to start bringing costs down with injection molding. Also, for the entire current product line, there's only one arm. So instead of having 8 different arms like we did in the last generation, there's one arm to rule them all at the moment. Both the leader and follower arms are made out of the WidowX AI. Some of the things that we're working on though is we're working on lower cost leader arms, because you don't need all this muscle in a leader arm. You only need to be following a person's trajectory. So we're working on shrinking that down, which will bring costs down on half the package if you have 2 leaders and 2 followers. We're also working on a 7 DOF human arm, essentially the size of a human arm with a 3-1-3 servo layout. And that's gonna have a whole different set of servos in it. You have much bigger, stronger ones at the top, obviously, and getting smaller as you go down. And then we'll probably take what we learned from that arm and make a pro version of the WidowX AI. So it'll be a tabletop that's got beefier servos in the base as well. So it'll have even higher payload and lower gear ratios, because these still have 40-to-1 gear ratios in some of these joints, and researchers want us to bring those down as well. So that's where the future of the AI line is going. Well, that was fun. Thanks for going through my journal with me. That's literally the last 20 years of my life. It's kind of wild to see it all on one desk. Going from this all the way up to something pretty like this. I mean, look at, my God, was this thing ugly. We did know it was ugly at the time though. It's not like we're just realizing that now. You can see the evolution here all the way through, from humble beginnings where you don't have as many resources to create something, where you have to be very creative and think out of the box and just sort of use off-the-shelf components, to being able to customize stuff. I'm really excited about where we're going in the future. So we have mobile manipulators, human-sized, you know, it's like wheeled humanoid robots. I can't believe that we're actually making that in this company. So that's where we're headed, and hopefully in another, I don't think I should be another 20 years, let's say in 5 years I can do another one of these videos. Thanks for watching.
Trossen Robotics, helping innovators innovate.